Hello and welcome to this presentation. Today we're going to be talking about 9 ways to secure your graph. So you've gone ahead, built, tested, and deployed your graph. Congrats. It's out there on the internet. And anytime something is out on the internet, we have to ask ourselves the question, what could go wrong? A lot of things. We have to worry about malicious actors, and this is anyone or anything out there attempting to disrupt or steal information from our application. We should also be concerned with the performance of our operations. Ideally, we'd like to know if and when things are going wrong in production, and we'd like to know as soon as possible instead of having to wait for our users and customers to tell us. By default, in GraphQL, our schema is publicly visible to anyone on the internet. While that can be useful to get started, it does give everyone, including those interested in messing with their graph, easy access to all possible operations. How can we decide who gets access to the graph? Also in GraphQL, we don't have the concept of versioning. That's because we treat the graph as a single source of truth, and when it needs to change, we change it. However, we don't want to break dependent clients when we change it. This means we'll need a good deprecation story. You know, there's a number of other well-known GraphQL related exploits. Have we thought about those? Things like query depth, breadth, sanitization, pagination, and so on. Are we handling these things in a secure way? So in this talk, we're going to be focused on establishing a baseline for production graph security. Breaking everything we have to discuss into 3 high-level categories: auth, reducing the attack surface area, and operations and governance. We'll take a look at 9 different graph security topics. For each, we'll discuss strategies and share resources that can help you feel more confident about your graph's security in production. All right, let's get into it. So the first category of security we'll cover is auth. You probably already know that auth stands for 2 things. Authentication, which is concerned with verifying that you are who you say you are, handling sessions and retrieving session state. And then there's authorization, which is the aspect of security concerned with determining what you're allowed to do. Authorization asks, what permissions and capabilities do you have? What resources are you allowed to interact with? And to what degree? So with authentication, what we're really focused on is maintaining the user's session state. That means we'll need some way to tell if the user is logged in, and we'll need to pass that state through to requests. The common pattern is to assign an authenticated user a JWT. This is a JSON web token, and to accompany requests with it. In the example shown here in the Apollo server instance, from within a single place, we can pull the token from the header, which contains session state for the user, and ready it onto the context object for further use in resolvers. For example, if we wanted to fetch the currently authenticated user's profile, we could do so by reaching into the context object, getting the user's session information, and utilizing it to resolve the request in the resolver. Writing auth logic in resolvers isn't the only way to set up authentication. We could also handle this logic in data models, custom directives, or even perform this work outside of GraphQL. We could do this in, for example, a use case where our downstream service is a RESTful API. In that case, auth logic is already built into the RESTful API, so it may make sense to merely rely on that logic instead. Authorization, on the other hand, is about determining if we have permission to perform a certain operation. One way to structure authorization logic is to determine a set of roles, like admin, editor, contributor, or subscriber, and then give those roles permissions. For example, an admin might have the edit page and edit others page permission, but perhaps an editor only has the ability to edit their own page. That is, they don't have the edit others page permission. So there's a wide variety of places you can put authorization logic. You can wrap resolvers, let the downstream service handle it, use middleware, or use custom directives. It's hard to prescribe a particular approach because there's not really a one-size-fits-all approach. It really does depend on your use case, the architecture, and perhaps even your experience level. One of my favorite talks on this topic is How to Auth by Mandy Wise from last year's GraphQL Summit. You should definitely check that out. In that talk, we take a middleware approach, hooking up auth rules using a community tool called GraphQL Shield. One other resource I recommend is if you're thinking about building authorization policies from scratch and you'd like to see a real-world example of how to think about structuring them, take a look at the WordPress rules and capabilities page. It's actually a really good inspiration for getting started. All right, so even with authentication and authorization covered, the overall attack surface area is still sufficiently large. Moving on, in this next category, we will discuss potential issues and techniques to protect both the performance of your graph and the data behind it. So tip number 3 is called mitigating malicious queries. One of the best things about GraphQL is the declarative nature in which we can ask for what we want. Because of the various entry points available to create a query, in addition to how we structure relationships, we could make it possible to write some inordinately deep queries. Like in the example shown here, such a query would certainly impact the performance of a production server, disrupting it or even taking it down. So that's no good. What should we do instead? Well, we want to limit the query depth. There's a useful package you can npm install called GraphQL depth limit. With it, you can limit the maximum depth of queries to, say, 5 or 10 or something. It's unlikely we'll really need such a deeply nested query, and if we do, we should probably take a look at how to design our queries in a more performant manner. This doesn't really just end with query depth. Pagination is also something we should handle with care as well. For example, if we were to return the first 100 authors and each author had 100 posts, a query like that would undoubtedly slow down if it doesn't DOS the server. To prevent this from happening, we recommend using pagination when appropriate, capping the input number in your resolver, and using a library like GraphQL input number to limit the possible input size. With that package, we can change the value of the input type to be a specific min-max value. It's pretty neat, right? You can always write that min-max value logic imperatively in your resolvers, but I tend to like this declarative approach instead. We make the input type limitations a part of your schema, and we make the implicit explicit here with this approach. Validation and sanitization. These are standard web application security practices. When you accept data from a user, one should always expect that the user-provided data could be malicious. There are 2 especially malicious techniques in this area, and they're called data exfiltration and data destruction. Data exfiltration is when a client writes a malicious query containing SQL or NoSQL code that tricks the database into returning more data than was originally intended. For example, the unsanitized query shown here could trick a SQL-based data source into returning all of the fields for a user, including their email and hash password. That's pretty scary. To prevent this vulnerability, we recommend following the usual rules for web application sanitization, in addition to the OSWAP GraphQL specific recommendations like reject invalid input without giving away too many details, leverage the GraphQL schema to support validation, and beware of using JSON scalars because they're a lot more prone to malicious queries if they're not properly sanitized. Okay, so the next tip is to use timeouts. When we request data from downstream services or data sources, there are a various number of reasons why they may take a long time to respond. The service could be down, queries may be expensive, or something else might be going on. Regardless of the reason, we don't want a graph request to hang for too long, waiting for a response. To prevent this, we recommend using timeouts to keep slow or unresponsive services from impacting performance for subsequent queries. Timeouts can go in resolver functions using REST data source, and in a federated context, they could go on requests to the gateway's node HTTP server. And you could also utilize a pattern similar to what's shown here, where we build our subgraph data sources with a fetcher object that says, for each subgraph, anytime we fetch data, set a max 3-second timeout for requests. Makes sense, right? Next up is rate limiting. Rate limiting is when you dictate how many requests a client can make per some time. Often we use rate limiting to prevent brute forcing login details, scraping data, or denial of service attacks. To implement this, there's an npm package you can download off the internet called GraphQL rate limit, but also we recommend taking a look at the approaches done by GitHub and Shopify. In both the GitHub and Shopify approaches, it leads to the topic of something called query cost analysis, which is our next tip. Query cost analysis is a way to rank an operation's complexity, to give it an overall score, and then look at the complexity score before deciding if we should execute the operation or not. To illustrate, take a look at the query presented here on screen. Even if we use query depth and something we'll learn about later called query mount limiting, it's still possible to overload the server with semantically expensive queries. Sometimes we just can't look at the depth or the potential amount of nodes to know if an operation is going to be expensive or not. With the query cost analysis npm package, you can analyze operations for complexity and block them if they're too expensive. So, for example, you can say, we will at most allow operations of cost 1,000 to execute in our graph. No more than that. Then you can annotate your schema using directives and assign costs to your graph operations. When a query comes in, the package tallies up the cost, checks the max cost amount, and decides if it's allowed to execute or not. That's pretty neat, right? All right, the next tip here is called safe listing operations. During development, it's really useful to be able to connect to your graph and then write whatever kinds of queries you need in order to populate and hook up components you're building. However, in production, we may not want to expose that same level of flexibility. Why? Well, we saw what's possible with deeply nested queries and overly complex ones. What if there was a way to just specify the exact queries that need to exist so we could just mitigate that problem altogether? Theoretically, if we have two different client apps, can't we just tally up all the operations from both apps and only allow those specific operations to execute? We can. The feature that enables this is called Operation Safe Listing. You can maintain a list of approved operations, and to set this up, you have to do a couple of things like registering your graph to Apollo Studio, which we'll talk about more momentarily, register the operations from the clients, and then add the operation registry plugin to Apollo server. You can check out the docs on Operation Safe Listing for more details on how to do this. All right, now we're on to tip number 4, and this is to limit API discoverability. And the first actionable step we can take is to turn off introspection in production. Now, introspection is useful. It's primarily used in the development stage as well, and we use these introspection queries to power our tooling. And that tooling does code gen, query building, and so on. However, the first thing someone may do when trying to exploit your graph will be to send an introspection query because this is the quickest and easiest way for them to learn everything about your schema. And with Apollo Server, if node env isn't set to production, introspection in GraphQL Playground will be enabled by default. So here we have an example of the steps a bad actor may take in order to learn more about your graph so that they can exploit it. As we can see here, if you have introspection turned on, then you've just made their work a lot easier. Without it, they'll need to capture requests from the client application and use those to try to piece together more details about the GraphQL schema. So disabling introspection is an important first step in making their lives more difficult, but it's by no means a definitive security practice. From here, we can see how important it is to decide what other protective measures you want to have in place, such as Operation Safe Listing, as we just previously discussed. So a side effect of turning off introspection in production is that we shut off the ability for all developers to point to the production graph URL to power their tooling, learn about the schema, and query for data in production. You'd still want the ability to do these things, but we just don't advise doing it through your production graph URL for the reasons we mentioned earlier. There's also a cost argument here. If you've got a very large team and you're constantly pinging your production graph, this could add up in cost. So what gives? What should we do? How can we get the best of both worlds? And when I was talking about Operation Safe Listing, I said the first step is to register your schema. And this is quite an important logical next step that we advocate for. It's to use a schema registry. What is a schema registry? Schema registry is a place that acts as a single source of truth for registering and tracking your graph. Similarly to how you track your source code with Git, a schema registry does the same thing, but with your graph. You can protect and keep track of how it changes over time. Once you register your graph to the Apollo platform, you get access to a number of helpful schema management, governance, monitoring, and querying tools. Specifically related to exploring the schema's shape and data, Apollo Studio has the Explorer, which is a GraphQL IDE, which you can use to build queries, explore data, and work on local development graphs. The Schema reference, which is an out-of-the-box documentation page that lets you see the entire schema's queries, mutations, types, and so on. And there's also the README page, which is exactly what you think it is. It's a way to onboard new developers to your graph and present them to everything they need to know about getting started, testing, and running your graph locally. We'll talk a little bit more about this and some of the other security-related features in Apollo Studio a little later. So continuing with ways to limit API discoverability, the next area is masking errors in production. When the server or downstream service errors occur, we probably don't want the client to know all of the intimate details involved with what went wrong. Informing the client about error details in the server exposes the current server vulnerabilities and opens the door for more concentrated attacks. So for example, the error shown on screen here errored out for reasons that have to do with the source code. It just wouldn't be wise to leak this all the way up to the client, because if we're not careful, we could also accidentally reveal other infrastructural details like the types of caches or databases we're using as well. To prevent this issue, we should swallow errors before they get a chance to get to the client. In Apollo Server, there's a format error API on the config you can use to accomplish this. But it's also important to take note of what's an error and what's an exception. Exceptions are, for the most part, expected and application specific. And exceptions, however, are infrastructural in nature. They're fundamentally unexpected. So clients don't need to know the specifics of exceptions, but they definitely need to know about errors. I highly recommend looking into using unions for modeling errors, making the implicit explicit, and declaratively giving application level errors the love they deserve at the GraphQL layer. Unions also force client code to handle errors as well, which I see as a design plus. The next tip is to avoid schema auto-generation. Many tools will auto-generate a GraphQL schema based on database tables or an existing RESTful API, for example. While these tools tend to speed you up in the short run, they make it very easy to guess fields on root operation types based on CRUD patterns. We recommend following the principle of a demand-oriented schema, which you can learn more about at principledgraphql.com, but it says that you should build your schema tailored to what the client needs are and to do so by hand. Because a demand-oriented schema is custom built, it benefits by reducing the predictability of a graph's structure, thus reducing the attack surface area. Number 5 is batch requests. We talked earlier about query depth, which was showing how you could write some really nasty, deeply nested queries. Well, you can also write wide queries, queries with breadth to them. Clients sometimes do this to perform batching, which is executing a number of operations at the same time. And while that's okay, someone may attempt to use this GraphQL feature as an exploit to purposefully disrupt performance and scrape as much data as they can, or to attempt to mitigate rate limiting. Okay, so here's a really good example. Say we're rate limiting our graph, and depending on the library or the way that we've set it up, a request like this, one where we brute force login attempts through a single GraphQL operation, may still get parsed and executed. So a combination of rate limiting and query complexity analysis can help to mitigate this particular concern. The other thing that comes up with batching requests is the fact that we may actually unintentionally DOS ourselves. If you're resolving data from a backing data source, like a RESTful API or a subgraph, you'll want to make efficient use of the network to prevent DOSing yourself. One technique is to make use of data loaders. This is a tool that minimizes the number of requests to backing data sources from resolvers through batching and caching. Speaking of caching, also consider using caching as a way to mitigate the number of requests you need to make overall. When we hear the word caching, we may think of it at a variety of different levels, like the client level, the gateway level, or the data source or subgraph level. All of these are valid, and you're free to try any combination of them. Okay, so the last category of security we'll discuss is called operations and governance. This admittedly covers a large surface area of topics, so we'll discuss the 3 big ones. The first is stability. So again, by design, GraphQL is not a versioned API type like REST. And ideally, you'd like to make changes to your graph, deprecate fields, and evolve it over time. However, once you've got clients using your API, whether it's REST or GraphQL, we just can't go ahead and make changes without notice, can we? The question is, how can we do this safely? How can we prevent accidental breaking changes? In Apollo Studio, there exists a feature called schema checks. Schema checks help you identify breaking changes before you make them, and they help you identify when a potentially dangerous change won't break anything. There are 2 types of checks you can perform. The first is checking operations, which verifies if your proposed schema changes will break any of your graph's active clients. And the second is for composition checking. This verifies that for a change to a subgraph in a federated architecture, your graph will successfully build when composed with your other registered subgraph schemas. So to not break prod, if we change some fields, we could see what the traffic looked like for that particular field, and we could see what client relies on it before we actually go through with making the change. This is the type of feature that makes sense to have set up in a CI. So before you push a change, you can make an informed decision, talk to the right folks, and coordinate your efforts in evolving your graph. Number 7, managing graph access. As we discussed earlier, we probably don't want our production graph to be available to everyone, so we turn introspection off. There is a way, however, to safely manage graph access for teammates, non-developers, consultants, and pretty much anyone in your org, given you'd registered your graph. In Apollo Studio, you can add admins, consumers, observers, contributors, and so on, making sure that users have the correct level of access to your graph. We further improved that this year with more granular capabilities to set either org level roles that go across all of your projects and graph level roles for specific graphs. In addition to the user roles, we've rolled out the ability to make your graphs either public, private, or protected. Public means anyone can access it as long as they have a link to the public variant. Private means they can't, and protected means it can only be modified by org and graph admins. As I mentioned before, there's the public README page, which can come in handy for public graph variants. Additionally, if your graph is public, you can take advantage of the recently launched Embeddable Explorer feature. This lets you embed an Explorer instance into your docs or your website as an iframe, instead of having to come to Studio to query a public variant. Number 8 is about observability. At any point in time, there's a lot going on with our graph. From the gateway to the subgraph resolvers to the data sources and beyond, we need a way to keep track of what's going on, especially if there's performance issues. We can make use of observability in Apollo Studio to investigate our graph's usage at the org, client, field, and operation level. Client awareness is a feature that lets you view operation metrics split per client, helping you understand how each one interacts with your graph. We advocate for requiring clients to identify themselves to your graph in a consistent fashion so that later on we can take a look at API usage and make sense of what's going on. Drilling down even further, we can get field level tracing for a detailed breakdown of how our graph's resolvers are performing. And we could also configure alerts to push notifications anytime something goes wrong, whether it's an increase in requests per minute, changes in your P50, 95, or 99 response times, or errors in your operations run against your graph. You can also check the Errors tab to see a record of operation errors and the reason for failing. If you want to leverage error data outside of Apollo Studio as well, you can use Apollo Server plugins to integrate with other APM, this is application performance metrics, tools like Sentry. Lastly, understanding your graph usage is important, but at the org level, you'll want the ability to keep track of key actions performed and by whom overall. Audit logs is a feature that lets you export a data file with all of the actions that were taken throughout the org. That means if there was ever an incident, you can export an audit log for a time period and see what actions an individual or an automated system has taken during that time. That was a lot. So now, in conclusion, we've covered 9 ways to secure your data graph. The first being auth. The second, focusing on reducing the attack surface area through thinking about how to handle malicious queries, limiting the discoverability of your graph while still enabling you and your team to carry out key use cases. And 3, figuring out how to safely deal with batched requests and prevent brute force attacks within them. And lastly, we talked about operations and governance. Ways to ensure that once your graph is up and running in production, the life cycle of evolving, monitoring, observing, and managing access to your graph runs smoothly. I hope this was helpful and that it inspired some ways to secure your graph in production. That's all for me. I'm Khalil Stemler, and you can find me at StemlerJS. Cheers.